Hey, everyone. Thanks for coming to the colloquium. Today we have Brenda joining us. Let me give you a very brief introduction before her talk. Brenda started her academic career at Brown as an undergrad student. Her concentration was chemical physics. She graduated with honor and went down to Columbia University to get her PhD degree. And then she moved to the West Coast as a distinguished Lawrence postdoc fellow. And then we are fortunate to have her back in the chemistry department. So today she just traveled across the Brook Street to give the colloquium. As a physicist, I can say that Brenda's work has been highly impactful to a lot of my colleagues in this department. I think today she's going to tell us a little bit about some of these work. So without further ado, Brenda, we're excited that you're here, and we look forward to your talk.
Great. Thank you, Leo. Thank you for the introduction and the gracious invitation to come speak to you today. First of all, what I should say is as Leo suggested, I do have a history back in this department. I was a chemical physics concentrator, and so, in fact, I've sat in this room many times. And in fact, my first introduction to physics, at least at a college level, was with Humphrey Maris back in the day. And so Humphrey was an amazing person. I John with Humphrey for several years. And one of the most memorable things about physics that Humphrey told me was, one day I was in his office, and he says, oh, Brenda, my back is aching. And I say, oh, I'm really sorry to hear that. And as like Humphrey would normally do, Humphrey basically said, Brenda, that's not a bad thing. If my back didn't ache, I wouldn't actually know how old I was. And so since that time, I've actually realized much of the truth of what Humphrey would tell us. Humphrey also had a lot of knowledge about how to teach physics. So whenever things got boring, he would bring out the monkey. I don't know how many of you know the monkey experiment. So in Phys 70, he would basically attach a monkey here and then drop it. And then try to hit it with some arrow. It had absolutely nothing to do with any sort of thing we were talking about in Physics 70, but it was always fun to sort of watch the monkey dropping. I mean, we could have solved a trajectory or a problem like that, but that actually never happened. We just dropped the monkey. It was always fun physics. And I also had the pleasure of taking classes with Jim as well. Jim taught us essentially what it was to be a teacher. Jim was absolutely phenomenal, and if you haven't been in some of Jim's classes, I would highly suggest that you take them. So suffice it to say, thank you for inviting me here today. It's good to be back. And since I've been back, my group has worked on three primary areas. We thought a lot about quantum statistical mechanics, a lot about computational biophysics, and a lot about alternative computation. But today I'm going to focus on the first area, because this is probably closest to you. And in this area, what we try to think about is how do we accelerate quantum mechanical methods using the techniques of statistical mechanics. And more specifically, what we try to do is solve Schrödinger's equation not only accurately, but very, very rapidly. And so you might say, why would you want to do that? There are plenty of reasons, and the key reason that I'm going to focus on today is that what we want to be able to do is to actually treat the physics of materials from a first principles level. So as many of you are very familiar with, historically in physics, we tend to think about low energy models, maybe things like the TJ model, the Heisenberg model, the Hubbard model. These models are incredibly powerful models, but they really don't tell us everything about the materials that we care about. This is a material I'll talk about later today. This is chromium triiodide. And if I try to map this into a model, it's going to give me a very simplistic representation of chromium triiodide that may not actually tell me everything I need to know to predict its properties over different length scales and potentially in different situations. So the motivation for this is sort of thinking about what we do in conventional physics. So at least historically, what we've done is we usually take materials, and these materials are fascinating in some regard. They stirred some amount of interest, display some type of interesting phenomenology, and we think about what are their essential principles. So I'm picking YBCO. Maybe that's not the best choice, but of course many of you know the history of YBCO here. So YBCO, as you can tell, is an incredibly complicated material. So it has a lot of copper oxide, so it has this copper oxide plane, but it also has barium and yttrium and other elements and a variety of different defects that make it become a superconductor in different regimes. This, at the time, was incredibly difficult to understand. And today, if I want to take this and try to understand this, put this on a computer, this would still be very difficult to understand. And so what people historically did is they tried to map this into a model. And so the model that at least many people thought, certainly people like Anderson thought would represent this material is the Hubbard model. So for those of you who are not familiar with the Hubbard model, right, the Hubbard model consists of a bunch of sites. These sites are supposed to represent these copper oxide planes. And on these sites, electrons can either hop around or they can repel each other if they exist on the same site. And the idea is that if you could figure out all the physics of this model, you would understand everything here, right? And so if you could solve this model, you would have immaculate understanding of what's going on in this material. Now, as many of you know, it's been very difficult to solve the Hubbard model even. And what that means is that it's actually very difficult to comment on even these materials. And so this has been the general framework that condensed matter physicists have thought about. But the problem here is that even though this might bring us understanding, it doesn't necessarily bring us everything. And so maybe just to give you a couple of examples, in many situations in modern times, what we really want to do is instead of saying, here's a material, why don't we figure out what it does, usually we have some purpose in mind. So here are two examples. Maybe we're thinking about batteries, maybe we're thinking about photovoltaics. And we want some sort of property out of these. Maybe we want a very high energy density battery. Maybe we want a photovoltaic that's lighter, maybe very flexible. And so we have properties that we want, and we want to find materials that are going to have those properties. And so the issue is that usually the framework that we're in today is that we typically want something. So maybe we want some sort of superconductor, we want a fast charging capacitor, maybe we want different things. And we're trying to find the materials that will give us those different things. And so maybe you could use those models to tell you something, but the key point that I want to make today is that it's actually very difficult to say from this model what material you should actually make that would realize your different properties, right? So if I look at a Hubbard model, it has a U, it has a T. That's telling me basically about my bands. It's telling me about my electron-electron interactions, but it's not telling me exactly what atoms should I put together to realize this kind of physics. And so if we want to be able to design different materials, if we want to seek out different new applications, it's very important that we actually be able to describe these materials from first principles so that we can then make predictions and potentially screen these different materials very rapidly. So just to give you two examples, and I'm going to steal an example from Leo, just because it's not only Leo's, but because it's actually also extremely fascinating. Here's a set of 2D materials, and if you're not familiar with Leo's experiment, he could probably describe it better than me, but this is a 2D heterostructure in which he puts bilayer graphene together with tungsten diselenide. And when he puts these materials together, he sees ferromagnetism emerge. And this is kind of an amazing thing, because if you just look at graphene and you just look at tungsten diselenide, right, you're not going to see any magnetic order emerge. And so that's an absolutely amazing property. But the key thing here is that if I replace this tungsten diselenide with, let's say, graphene, or maybe I replaced it with a different material, I'd probably have a completely different outcome, certainly in different parameter regimes, right? And so it's very, very important that one actually be able to describe at an atomistic level what's going on in these different situations. Another example of where we actually need this kind of detail, we can't just rely on a model, is when thinking about quantum computing. So I'll just provide one example. There are many, many, many examples in quantum computing where a simple model is probably not going to tell you what you need to know about decoherence, et cetera. But here's one example. So several of us in this department have interfaced with IonQ in different ways. And in one way that I've worked with the IonQ team is thinking about ion-trap quantum computers. So IonQ makes these computers. They have incredibly high fidelity gates. But the problem with these gates is that they do experience some decoherence due to motions that they pick up as a result of something called anomalous heating. So this phenomenon of anomalous heating, for a long time people had no idea where this actually came from. But this comes from very, very specific material interactions. So as it turns out, on the surface of these quantum computers, so on the surface of these chips, there tend to be molecular absorbates that get absorbed onto that surface, and they move in very, very special ways that actually heat up the ions above this trap. And as a result of that, result in a great deal of decoherence. And so the point is, if I tried to make a model of this and I actually didn't know what was going on molecularly, I wouldn't be able to describe the kind of heating that's going on. In fact, many people spent a lot of time making models but couldn't tell you what physically is actually going into the situation to cause this kind of heating phenomenon. And so what this means is that we really do need to understand, for many modern purposes, the atomistics that go into many different physical situations. Because if you ignore the atoms and you don't really understand what's going on, you lose a lot of the essential ideas and the essential things that are happening. So for years, physics has focused on a variety of different models, and physicists have prided themselves on this. But this is a case where essentially chemistry comes to the rescue. Maybe that's a dangerous thing to say in physics departments. They never want to think that chemistry comes to the rescue. But chemists have been thinking for quite some time about how do we bring reality into our systems. And so maybe I'm giving you a hyper-fetched example, an over-fetched example of a chemical type binding model. You can imagine maybe I have some molecular system that looks like this, and it kind of looks like a Hubbard model. There are better models of this. I'm sort of making a joke. But if you think about what happens with this kind of type binding model, what kind of chemistry it would give you, most chemists would just kind of stare at you, right? So you look and you say, what does this represent? Well, this could be ammonia, this could be phosphine, this could be anything. And so chemists have long dealt with this issue of bringing material reality into their different models. And that's because, fundamentally, if we want to describe chemistry, we have to do it with incredible levels of accuracy. So oftentimes in chemistry, we talk about something called chemical accuracy, which people tend to say is about 1 millihartree. So that's oftentimes less than 0.01 eV. That's a key benchmark for us. So if we cannot reach that kind of level of accuracy, we oftentimes cannot describe reactions, and we certainly can't describe kinetics. And so chemistry has come to the rescue in many regards for trying to understand materials properties from a perspective of realism. And a lot of that started back, even as far back as the 1960s. And so this is something that people don't tend to talk about, but it's sort of what I call a slow, quiet revolution. So way back in the 60s, many of you know that Walter Cohen came up with density functional theory. And maybe a little bit afterwards, John Popel started to think about different types of wave function theories. And so they thought about these theories. They were theorists, and I was surprised to actually learn John Popel considered himself a mathematician at one point in time. But they were theorists who wrote down different types of theories, and for this they won the Nobel Prize in chemistry in 1998. But with the advent of supercomputers, what we were able to do since then is actually take their theories and build them up into large-scale models of essentially how molecules behave at the very fundamental level. And so as a result of this, over the past several decades, some of their initial theories thinking about how do electrons behave and how we can represent them have grown into a whole industry of a variety of different theories. So things like full CI, physicists usually call that exact diagonalization, mean field theories like density functional theory and Hartree-Fock, perturbation theories, Monte Carlo theories, renormalization group theories, and many different types of methods that now allow us to describe chemical systems with incredible levels of accuracy. So I kind of joke to people that this is the electronic structure tower of Babel. There are a ton of different theories, just theory after theory after theory. If anybody ever reads this literature, I know many of my students have gone through it. There are just so many acronyms and so many different theories that are out there. But the fact of the matter is that these theories have provided us with a way of describing things with such a level of accuracy that we can really talk about what materials are doing at a fundamental level with a very high level of description. So just to give you an example of what these kinds of theories and what this quiet revolution has brought to us, I'll pick a couple of examples from my group and from others. So this is an example from my group. Here we're interested in trying to understand the binding of an electron extremely far away from a molecule with a dipole. These are actually experiments that are done in the chemistry department. If you're familiar with Lai-Sheng Wang's experiments, he's sort of the world's expert on anion chemistry. And what happens in these systems is, as Teller first predicted, if you have a molecule with a dipole, it can actually bind an electron extremely far away. But if you think about such a system, and you have an electron that's so far away, you can imagine that that electron binds very, very weakly, actually at the level of 100 inverse centimeters, right? This is an incredibly small energy scale. And so you might say, can anyone actually predict this? Well, because of this quiet revolution that's sort of bringing reality into different descriptions of physical matter, we can, in fact, predict these kinds of binding energies, which are incredibly small. So these are a variety of simulations from my group, actually, where we developed some new methods where we can actually predict binding energies of the order of about 10 inverse centimeters. Incredibly small energies that can tell us whether this electron is bound or not bound. Now, that might sound like maybe an esoteric example, but let me give you another example that I'll show you might be a little bit more relevant to this audience. So one example is the chromium dimer. I don't know how many of you have ever heard of this problem. This is a long-standing problem in the history of chemistry. So as you know, chromium has a number of electrons. If you bring two chromiums together, they'll bind. But they have an extremely interesting way of binding. So if you look at these curves down here, which I'll talk about in a second, this is essentially their binding curve as a function of bond distance. And what you'll notice, if you can see beyond all these different lines, is that this binding curve actually has two humps. So there's a deeper minimum over here, and then there's something that people call a shelf over there. And so for many, many years, if we go back to the 1980s and some of those very old methods, what you see is that they completely missed these minima, right? So they put sort of a minimum all the way out here. Maybe the bond is super, super long. But as these methods improved as a result of this revolution, what you can see is that these curves became more and more exact. And so the experiments on here, underneath, I can't quite see well from here, but the experiments underneath, and at this point in time, we basically exactly match experiment. We're able to get both minima, the first minima coming from 3D orbitals overlapping, and the second coming from 4s. And we can do that with a level of accuracy that's about of the order of what I was talking about before, about 0.05 eV over the entire curve. And so this is sort of an incredible feat, but it brings the question up, and so we're able to do these things within chemistry regularly. Could you take these kinds of methods, so could you take the accuracy of the chromium dimer and use that to treat other kinds of systems, systems that are of interest to condensed matter physicists? So could you go from chromium dimer to chromium triiodide, for example, and be able to predict all the physics of this using the same basic principles that people are using to understand chemistry? And so this is sort of the grand challenge that we think about a lot in my group. We think about how can we bring these methods over here that have done so successfully well in describing the reality of chemistry. We haven't solved all of chemistry, but we can solve many things in chemistry. How can we bring that realism into different types of condensed matter systems? Now, I should say this is not easy, and I'm certainly not the only person who's been thinking about this. There have been a growing number of people thinking about this. There are many challenges that we face in doing this. I'll mention a few very quickly, and then I'll go into some of our approaches. One issue with doing this is if we want to describe these kinds of materials, there are many different energy scales, and that's probably the first thing that comes to mind if you're a physicist. There are high energy scales, there are low energy scales. Can you capture all these different energy scales? That's one of the key challenges. A secondary challenge is also how do you go to the thermodynamic limit? So we have to describe very large systems, right? These are solids. Hopefully periodic solids in most cases, but we still have to go to the limit where we're describing a large enough system so that we don't have finite size effects, and that can be a challenge in many situations. And of course, one last challenge is getting the electron correlation right. So we have a lot of electron correlation in chemistry, but we also have to get it right if we're going to be able to describe different types of condensed matter systems. So there are a lot of challenges along this road, but suffice it to say, I think many of us are making progress in this direction. And what I'll tell you about is some of the methods that we've been developing and a couple of examples that show where those methods are going. So what I'll briefly introduce you to are some of the types of methods that we use to solve this, which are what are called quantum Monte Carlo methods. These methods are what I'll call the stochastic state of the art. These are methods that try to solve the Schrodinger equation using random numbers. Although I didn't go into 2 quick vignettes, I'll see how much time I have. The first showing how we can start to construct finite temperature phase diagrams, so phase diagrams as you might see for superconductors from first principle simulations. And then the second vignette I'll tell you about is magnetism in chromium triiodide. So I showed you chromium triiodide before. It's a 2D material. But what we can do with these methods is we can actually show, with a high degree of accuracy and resolution, exactly what's going on in this material down to where electrons are at the sub-angstrom level. And then I'll summarize at the end. So let's start with exactly what kind of methods my group designed. So as I was saying, we're very much inspired by the computer-aided materials design principle. What we want to be able to do is allow computers to very quickly and cheaply sort through many possibilities for what materials we might be able to use to realize different properties. So as I was saying before, today we're typically interested in trying to find materials that give us different properties that we want to put into different devices. And the way this is typically done is we usually start out with either candidate molecules or materials, and then we go to simulation. The simulation can filter through these many different materials and these properties, and then take some of those screen candidates and allow us to do some experiments to confirm those properties and then iterate back. Now, what simulation has mostly focused on until recently has been density functional theory, particularly in condensed matter. Density functional theory is an absolutely great tool, but the problem is that it's not always right. And so I sort of call this trouble in simulation paradise. So for many, many materials, you can go through that cycle and have absolutely no problem whatsoever. But the problem creeps up whenever we start talking about what I'll call truly quantum materials, materials where electron correlation actually matters. And so these things consist of things like transition metal oxides, certain types of 2D materials, particularly those that involve DNF electrons, have strong spin orbit coupling, and that can also have a large degree of magnetism, and also things like lanthanides and actinides. In all of these situations, if you just run your run-of-the-mill density functional theory calculation, you can oftentimes get very, very wrong answers. And so what we try to do is find a balance between density functional theory calculations and much more accurate calculations. And so this is a principle that I was taught when I was much younger about coming up with methods. And this is by Richard Friesner, who's a professor at Columbia. Now he owns Schrodinger, if anybody knows that. That's a huge software company at this point in time. And so what Rich used to say is that what we deal with when we make methods is that we always have to deal with some level of conservation of annoyance. At the one end, we have theories like density functional theory. Density functional theory is a good theory in the sense of, so I'm not someone who puts it down. Density functional theory is a good theory in the sense that it provides you with some level of accuracy, but it does so at a very, very low cost. And so because of the fact that it's not always accurate, it can cause you some level of annoyance. But on the other end of the spectrum, you can have exact methods, which can tell you absolutely everything about a material, but they tend to come at very high cost. And so what this leads to is essentially conservation of annoyance. We have methods that are low cost, but low accuracy, and then methods that are high cost, but very high accuracy. And so where some of us actually like to sit is in this sweet spot right in the middle. And so the methods that we try to develop try to get the best of both worlds by sitting in that bridge in between. And so the methods that we develop are what are called quantum Monte Carlo methods. These are methods that use Monte Carlo in order to sample quantum properties. So I think many of you are familiar with Monte Carlo. Certainly if you're coming from physics departments, you've probably used Monte Carlo to solve things like the Ising model. Right? So in Monte Carlo, what you do is you generate random numbers, and those random numbers they're generated according to a probability distribution. And that probability distribution is usually designed to reflect some aspect of your system. So maybe it's designed to reflect sampling of a partition function or some other quantity. And so for decades, people have used these methods very successfully to understand classical physics. Right? So if you think about classical fluids, if you do think about, let's say, the classical Ising model, people have used Monte Carlo to solve these problems. In fact, Monte Carlo is pretty much the way that we solve things like classical proteins. Right? So if we want to understand what the structure of a protein is, we do a lot of Monte Carlo to figure out what that looks like. But much more recently, people like me have gotten interested in whether we can generalize these methods to more quantum systems. So you can imagine, instead of maybe sampling the positions of different particles in a fluid, instead you can sample what are the components of a wave function, or maybe what are the components of a density matrix if you're working at finite temperature. It's an interesting paradigm. It's an interesting thought. Can you actually use random numbers to solve these problems? And the answer is, of course, yes. Otherwise, I probably wouldn't be speaking to you. But it comes with a couple of handicaps. So quantum Monte Carlo methods happen to be very, very good in the sense that they have relatively, what we call relatively low scaling with system size. So they scale as about n cubed or n to the fourth. And this is pretty good because if you look at other methods, so if you look at things like density functional theory, that tends to scale like n cubed. And it's much, much better than the exact method. So configuration interaction is the method that I show on top, and that tends to scale exponentially. And so that's a good thing. But the reason why people sort of shrugged at quantum Monte Carlo for many, many years is because of something called the sign problem. So I don't know how many of you are actually familiar with this problem. It's a crazy phenomenon for those of you who are familiar with statistics. But what this comes from is essentially the fact that you have to sample negative probability distributions or even complex probability distributions in order to obtain the samples that describe your system. And this fundamentally comes from the fact the fundamental fact of the Pauli exclusion principle, where if you're exchanging two electrons, that's going to change the sign of your wave function. And so for many years, people sort of grimaced at quantum Monte Carlo. If you have to sample these negative numbers, a negative probability distribution with a positive probability distribution, how are you ever going to get any information out? But suffice it to say, over the past 10, 20 years or so, these have actually become some of the premier methods for solving many problems. And that's because we've come up with new ways of curbing this problem. So we either mitigate it significantly, or we control it in different fashions so that it doesn't arise. So let me show you a couple of things that have come from this. So back in the day when people talked about the sign problem, they shrugged because when you had to deal with it, you'd sort of get energies that are like this. So maybe you would look at Hartree-Fock, which is a fairly mild mean field theory. You compare it to the exact answer, and Monte Carlo would be somewhere in the middle, not particularly good, and potentially with reasonably large error bars. But today, with different types of techniques, you can do the kinds of examples that I mentioned. So here's the example that I mentioned earlier of things on the order of 100 inverse centimeters. But you can also look at things like the Hubbard model. So my laser pointer is going in and out, but the quantum Monte Carlo methods for the Hubbard model are now among some of the most accurate methods there are for solving these kinds of systems. And so the message that I'm saying here is that quantum Monte Carlo is one method, is one path to actually being able to solve many of these problems with extremely high accuracy and yet very low cost. So let me give you two examples of those methods at play, and let me show you exactly how they're trying to bring realism into different condensed matter systems. So as one example, I'll talk about some of our group's work trying to develop an ab initio finite temperature auxiliary field quantum Monte Carlo method. There's a lot of words in there, but what we're trying to do is we're trying to make a method from first principles that can predict finite temperature phase diagrams. So let's say we have a system, we want to understand its free energy. Can we predict that as a function of temperature from first principles? And the reason why we'd be interested in finite temperature is a fewfold. So number one reason is that in many planetary astrophysics and geophysical systems, you'll have molecules or materials that are brought up to extremely high temperatures, but also extremely high pressures. And in those situations where you have a combination of high pressure and high temperature, many electrons will be excited to very, very high energy states. And as a result, you have to start thinking about how temperature is affecting your electronic degrees of freedom. Much more recently, there have been a lot of experiments, which I'll roughly call laser-induced chemistry or laser-induced plasmonics experiments, where people think that by using a laser, it's basically depositing heat into the system that allows electrons to traverse different reactive pathways than otherwise. And so for these kinds of experiments, you'd actually want a finite temperature theory to describe them. But last but not least, and this is the key example that really motivates my work, is that we want to be able to describe solid-state phase diagrams. So much like the cuprate phase diagrams, or maybe some of the graphene phase diagrams that people are interested in this department, what we really want to be able to do is take a material and then say, at temperature, what are the phases that temperature is going to exhibit? Is it going to be superconducting? Is it going to be an antiferromagnet? What is it going to be as a function of temperature and other parameters? And so, again, this isn't necessarily a new paradigm, but the new paradigm is really bringing in first principles and bringing in realism into this description. So as I said, in the ground state, there are a ton of different methods that people have come up with for these different purposes. But what interests me as a theorist is that there were basically no methods before we started looking at this. And so, I can put no methods with an asterisk. There were methods, like you could solve the exact problem, so that's ED at the bottom. You could do mean field theory. And there were some Monte Carlo methods somewhere in the middle, most of which couldn't really touch base with realistic materials. And so when we started this is sort of the picture. This is what we had in terms of methods that could accomplish the tasks that we want. Since that time, I'll tell you, since we first published our paper, many, many more people have gotten into this field. And so let me tell you a little bit about what our method actually does. So what we wanted to do is actually create a method that could work for any system and could do so at the first principles level, and it can incorporate electronic reality into the system so that we can solve its finite temperature phase diagram. And the way that we did this is by combining ab initio methods, so some of those methods from chemistry that I was talking about, with methods from the physics community. So if people have ever heard of determinant quantum Monte Carlo methods, I'll describe them in a second. We put the two of those together in order to get methods that could really handle first principles problems at finite temperature. So just quickly before I go into that work, I should just say this work was done, a lot of this work was done a couple of years ago by Yuan Liu, who's an incredibly talented graduate student. He's now a postdoc at Harvard MIT with Isaac Chung, and also Tong Shen. I was also fortunate enough to know Min-Sik Cho. Min-Sik was actually a freshman who helped with this project. As a freshman, he actually coded many of our initial codes. So I'm very thankful to all of them for their contributions to this. So how does our approach actually work? So as I said, what we do is we combine ab initio quantum Monte Carlo methods, which have been developed for the ground state historically, with finite temperature determinantal Monte Carlo methods. These are methods that physicists have used for many decades to understand different types of lattice models. Here I'm just showing an example of a phase diagram that people use this method on to understand quantum spin liquids. And so as you can see, what this method can do is, as a function of temperature, it can tell you a whole bunch of different phases. And so we wanted to take this realism and basically put it into these different types of methods. So to give you an overview of how this kind of works, I'll go through a little bit of the math, but I don't want to bore you with too much math. Determinant quantum Monte Carlo, which is a method from the physics community, was invented around the 1980s by people like Steve White and Hirsch. And the way this method works is that it basically takes a system and it breaks it up into either orbitals or sites. And on those sites, what you end up doing is you end up sampling a bunch of what I'll call fields. I'll tell you why these are fields in a second, as a function of imaginary time. So imaginary time is sort of a little increment in inverse temperature. And so as a function of imaginary time, what you do in this Monte Carlo method is you sample a whole bunch of fields. As you can see, these are what we call Gaussian distributed fields, right? They point up and down with different magnitudes that are Gaussian distributed. And you sample these fields again and again until you're able to actually reconstruct a finite temperature partition function. So why fields? Why does this all work? I'll just give you some of the basics. So what we want to do in these kinds of methods is we want to sample finite temperature observables. So maybe we want to get O over here. And the way that we would have to sample them is we'd have to sample a partition function. So here we're sampling the grand canonical partition function. And the way we have to do that, so the grand canonical partition function is trace of e to the negative beta h, essentially. The way we would have to do that is by breaking this up into small pieces. So what we do is we take that inverse temperature beta and we break it up into very small time slices delta tau. And the reason why we break this up is because we actually can't exactly compute e to the negative beta h. It's a very difficult quantity for us to compute because it contains lots of electron-electron interactions, two-body interactions that are very difficult for us to represent. And so we break these up into very small slices so that we can do a couple of special things. So the first special thing that we can do is something called a Suzuki-Trotter factorization. I don't know if people have studied this, if they ever took field theory. And so in this factorization, what we can do is we can split the Hamiltonian up into kinetic and potential pieces. So K is the kinetic piece, V is the potential piece. And once we can split that up, it turns out that we can express the kinetic piece exactly. But the potential piece is sort of the problematic piece for us. So if we look at a real Hamiltonian, a real ab initio Hamiltonian, that potential piece is the second line. So after that plus sign, you can see that contains many, many, many terms that are very, very difficult to understand overall. And so it's very hard to compute that exponential. And so we have to rely on something special. We have to rely on the fact that we can express that potential in terms of squares. And so it turns out that you can prove that you can express any general chemical potential in terms of squares of operators. And if you can do that, you can do something which is called the Hubbard-Shordanovich transformation. So some of you, again, may have seen this in field theories. What this transformation says is that if you take e to a square of a one-body operator, so these little v's are one-body operators, we can always express that exponential of squares in terms of an integral over one-body operators. So you see here, again, this would be where the pointer would help. You see here that I have e to the negative v on the right. And so that v is a one-body operator, or essentially a one-particle operator. And so I can take e to a bunch of two-body operators and represent it as an integral over a whole bunch of one-body operators that are a function of fields sigma. And so that's where these different fields, these red arrows, are coming from. If we sample all these different fields, we can put them into that operator, and then we can just calculate that one-body operator, since it's easy to calculate one-body operators. And so this sounds kind of tedious or maybe detailed, but the point is that this actually makes us able to compute a wide variety of properties that we wouldn't be able to compute before and to represent a variety of different types of physical systems. So we're able to put all that together, and we end up with a Monte Carlo sampling problem where we just sample the fields, like I said. And so what we do is in my group, we put these things together. We take a fully ab initio description of the problem. We take that potential in all its glory and all its pain. We decompose it into a number of different fields, and then we sample over all those fields as a function of imaginary time to reconstruct all of our properties. So let me show you a few results, and then hopefully we'll get to the last part of the talk. So when we first started looking at these different methods, what we wanted to ask is, can they tell us about simple systems as benchmarks? And so one of the first simple systems that we looked at is the nitrogen atom. And so I show this to you because it kind of tells you what should go on according to your intuition. So here I'm plotting the occupancy, so essentially how many electrons are in this nitrogen atom as a function of the chemical potential. We're working in the grand canonical ensemble, so we have to fix a chemical potential. And so what you can see is that as you bring this to low temperatures according to our method, you can see little plateaus develop. And those plateaus are telling you how many electrons are being occupied at these different chemical potentials. If our method didn't work, we wouldn't see any of these different types of plateaus. And so this is telling us that essentially we're working correctly, that we have a method that will tell us how electrons are interacting. But of course, we can go on to harder systems. So this is a little bit harder system. You might say water. Water's not so hard. But water actually does some interesting things here. So what we can do is we can take water, and we can model it as a function of inverse temperature. So just so that you understand, this is where it's not so good. Just so that you understand, so where the axis is 0, that means we're working at a high temperature. And where the axis goes to large numbers, so let's say 35, that means a low temperature. And so what you can see is that we can model across this entire temperature spectrum, and we can calculate things like the energy, the entropy, and different types of free energies. And so what you see is that at high temperatures, many methods agree on what's going on in the system. So here I'm comparing our method, which is in green, to exact diagonalization and mean field theory. And so at high temperatures, you'd expect mean field theory to basically tell you the right answer, and of course it does. You'd expect that because the electrons are not really talking to each other. At low temperatures, we also find that actually many of these methods agree, but it's in this middle regime where the temperature is not too high, not too cold, that we find that our results are a little bit different than what you would get from mean field theory. So in this regime, in this middle regime, you actually see the most correlation. You actually see that exact methods bring the most information about the system in this regime because the electrons have the choice of occupying some range of levels that's a little bit non-trivial, right? So they don't all occupy the ground state. They don't all evenly distribute themselves, but they do find themselves somewhere in the middle. And so our method in green can actually pick that up just as an exact method could. And so that's sort of a triumph of our method, and it's also a triumph of being able to show that we can model things first principles at finite temperature. Of course, we can go to harder systems. So here I'm showing C2. C2 is harder for a chemist just because it has multiple bonds. And again, we can come in line with exact results, which is the dotted line for the ground state below. But what you might say is, that's great. We can look at these different small systems. Well, what about solids? So over the past few years, what we've been trying to do is go from these small molecules to solids. Of course, we're not at YBCO, but we are at the point where we can actually talk about solids. So just to show you one example, right now we're working on a variety of 2D materials. To show you one example, for now, I'll talk about the 1D periodic hydrogen chain. And so this is a real material in the sense that we're treating everything, we're treating the hydrogen atoms as real hydrogen atoms. We're not treating them as sites. And the question we want to ask is what does this finite temperature phase diagram actually look like? Part of the reason why we chose this system is that many people have thought about this in the ground state. For quantum chemists, they think a lot about this chain to see if they get solids right or not. But we also wanted to think about it because it is, in fact, very much like a Hubbard model. So would we actually see any difference between these hydrogen chains and 1D Hubbard models, which people solved many, many years ago? So we looked at these different systems, and what we wanted to hopefully see is that there's some difference between the 1D Hubbard model and these hydrogen chains, and that's because there should be longer range interactions in these hydrogen chains than in the 1D Hubbard models. And so what we were able to show is that, in fact, we can simulate these systems. We can see that they basically get the same ground state structure. So if we come in at finite temperature, and we look for what is our equilibrium chain length as we go to lower and lower temperatures, we basically get the same result as one would get in the ground state, so somewhere around 1 angstrom. And we also see that the equilibrium energy is very, very similar to what one would predict. In contrast, if you look at mean field theories, they tend to be rather off, and they definitely get dissociation off. So if you look at this hump in the curve, we consider that in chemistry to be a very, very wrong thing. And so mean field theories don't actually get that right. More interestingly, what we can do is we can also look at phase diagrams, right? That was the whole point of this. Can we look at ab initio phase diagrams? And so we looked at things like the metal insulator crossovers that can happen in these different systems. So if you're familiar with these kinds of models, if you're in the high temperature limit, you should generally be in a metallic state. So the electrons can occupy any atom, any site at any time. And so if you think about the different states there are on a given atom, there'll basically be 4. So if you have 2 electrons, you could have no electrons on that atom. You could have 1 up, you could have 1 down, or you could have 1 up down on the same site at the same time. So if you're in a metal, the double occupancy, the probability that you'll have a double occupation, 1 up and 1 down on the same site, is going to be about 25%. And so what you see here is that at high temperatures, we are in fact able to pick that up. At virtually all chain lengths, so all separations between the hydrogens, we see that we're in the metallic phase. But as we go to lower temperatures, we see the onset of insulating phases. So this double occupancy goes downwards. It doesn't go downwards monotonically, and that's a whole nother story. But you see that it goes downwards, and we do, in fact, get insulators for these longer chain separations. And so that's telling us a lot about the physics, that we're actually able to see the difference between metals and insulators for these systems. Just to give you the contrast, again, if we look at mean field theory, it overestimates all of this. So it says almost everything's a metal, and that's not right at all. And so we're able to actually show these kinds of details at a level that others haven't been able to do before. Just to throw it out there, we can also look at things like different types of orderings, which I won't show today, but also things like heat capacities, and we can get different heat capacity curves. And one thing that we're grappling with right now is if you compare the curves you get for these hydrogen chains to what you get for the 1D Hubbard model, they're actually a little bit different. So from these early predictions for the 1D Hubbard model, and I should say these are for relatively small systems, maybe 3 or 4 or 5 sites, you see that people originally predicted that you get a charge hump and a spin hump. So at higher temperatures, you get a charge hump. At lower temperatures, you get a spin hump. We actually don't see 2 humps. We haven't been able to resolve that in our kinds of calculations. And so that suggests that either something interesting is going on between the charge and the spin and the hydrogen chains, or that you have to push to really low temperatures in order to see that separation. And so that's one of the things that we're trying to think about now. But at least lets us draw this contrast. We're at least able to say, this is what hydrogen chains do. This is what the Hubbard model does. What's the difference between them? Right? And we can understand what realistic interactions do to this original picture. So suffice it to say, what we can do is we can predict a variety of different finite temperature phase diagrams. We can see different phases, and we can also see different types of couplings, different types of effects, and different types of crossovers that others can't using first principles methods. So I'll come back to this in a second, but I just want to give you one other quick story, and then I'll wrap things up. So there I was showing finite temperature systems. We've been creating a variety of finite temperature methods, but we've also been creating a variety of ground state methods. And these methods are probably of most interest to you in this audience. So recently we've got into the business of trying to think about how we can understand 2D materials with a very, very high level of accuracy. Again, putting in all the real ingredients into these materials and seeing what we can actually predict in terms of phases and physics. And so one such material that we've been looking at is chromium triiodide. I introduced it a little bit before, but chromium triiodide is an example of a ferromagnetic 2D material. So if hopefully some of you are familiar with this, but chromium triiodide was one of the first 2D materials that was predicted to be a ferromagnet and have magnetism in its 2D limit. For many years, people argued about whether that could actually happen in a real system, because on paper, it shouldn't happen. But in about 2016, it was published in 2017, a couple of different groups discovered that you can, in fact, have the magnetic 2D materials. And so chromium triiodide was one of those materials. We since now know that there are many other such materials that will remain magnetic all the way down to their monolayer limit. So some of them are being explored in this department. But suffice it to say that it's become very interesting to try to understand what's happening in these 2D materials. These 2D materials, and I'll bring up Leo's example again, also pose an interesting challenge for us. So as modelers, these materials have correlation between the layers and within the layers sometimes. They have van der Waals interactions between the layers. Van der Waals is typically not easy to get using modeling principles, and they oftentimes also have spin-orbit coupling. But what is in our favor is that these are actually pretty small systems, right? They're only 2D. And many of their properties, if we're interested in things like magnetic moments, only require understanding what we call one-body properties. And so in our group, what we've also done is created a variety of methods so that we can understand the realism that's in these materials as well. So in the ground state, we've developed a suite of techniques so that we can actually look at the magnetism at very, very high resolution. And so this work was done by mostly Dan Staros in my group in collaboration with Ganesh at Oak Ridge. So let me cut to the chase just because we're running out of time here. And let me just say, what happens when you look at these different materials is you can go to density functional theory. You can go to these lower levels of theory and ask, what kind of properties do you get? And what functional should I actually use here? And this is a key motivation for a lot of our work. The answer is it's actually, if you use DFT, it gives you answers that are all over the place. So here I'm showing, if you look at chromium triiodide in the bulk, what density functional would actually reproduce the bulk lattice constant. So that bulk lattice constant is the vertical dotted line. And what we can do is we can test a whole bunch of functionals and say which one actually gives us that vertical line, matches the vertical line. And so in this case, maybe PB plus U equals 1 electron volt might give us the best result. That's just one type of functional. But what we can do is we can also move to other properties. So we can look at magnetic moments and ask which functional gives us the best magnetic moment. And if you do that, you get a completely different answer. And then if you look at other things, so let's say you look at the band gap and you say which functional gives you the best band gap, you get a completely different result again. And so as you can see, the problem here is that every single time you ask for something different, a different functional gives you a different answer, and there's no one functional that's telling you the correct information every single time. And so this is kind of a huge issue. And so for us, we went in knowing that and asking the question, can our methods, can these stochastic methods actually tell us what we should be predicting as opposed to just guessing which functional works in which situation? So for the sake of time, what I'll quickly say is that we use two slightly different types of stochastic methods here. I talked about auxiliary field quantum Monte Carlo before. Here we're using what are called real space quantum Monte Carlo methods. These are methods that work in continuous space. And the two methods that we generally use here are what are called variational Monte Carlo and diffusion Monte Carlo. So in variational Monte Carlo, what you do is you start with a wave function, and that usually has some set of parameters, and then you try to optimize those parameters to minimize the energy. So you sample and sample and sample until you get the lowest energy. Diffusion Monte Carlo, what you do on top of that is you project down to the ground state. So it's a complicated set of dynamics, but essentially what we do is we start with some set of samples, some walkers that are distributed, and then we sample what the wave function should be repeatedly until the walkers kind of bunch up close to the ground state. So anyway, we use these techniques within a code that actually I was one of the original developers on. So this is about a 15-year-old code now that DOE supports. It's called QMCPAC. It's the most advanced quantum Monte Carlo code out there. And we can use this code to try to understand the properties of these materials. So what we did is we developed a couple of methods to actually be able to understand what's going on here. So the first method that we worked on is something that tells us the geometry. So for those of you who are physicists and know about 2D materials, you might know that their geometries are not easy to predict, right? They can stretch out in many different ways. They can be perturbed by putting them on different substrates. And so actually getting the geometry right is not a trivial matter. So what we did to do that is we created something called a surrogate Hessian model. And so what this surrogate Hessian method does is we use density functional theory, which is quick, to construct a Hessian. And that Hessian can be used to tell us in which directions we should search to find the optimal geometry. And then along those directions, we'll put more expensive QMC calculations so that we can kind of refine exactly what that geometry should be. So this could sound familiar to many of you. You could use machine learning to do similar things, and of course our group has done that. But suffice it to say, what we can do is we can use kind of quicker methods to tell us exactly where to put our exact calculations to tell us where the lowest energy geometry should be. And when we do that, we came up with some very interesting results. So we started this study way before there were any experimental results on what the monolayer geometry should look like. And what we found is once we do our calculations, once we do this optimization, we can actually get lattice parameters that are essentially right on. So as we were doing this work, an experiment, this is Lee in the table here, an experiment came online. It was an STM experiment that essentially told us that our lattice parameter, 6.87, was basically exactly spot on to the 6.84 that people got. And so using these methods, we can get an incredibly accurate geometry. And then with that geometry, you can calculate the electronic properties. So if you get the geometry wrong, you'll get completely different electronic properties. And so once we got the geometry, we were able to actually get things like the magnetic moments and the electronic structure with very, very high accuracy. So once we had that geometry, we could run density functional theory, and we can run DMC, diffusion Monte Carlo, and we see that we actually get very close to the same moments. If we put in the DFT geometry, we got things that were completely different. So the DFT would give us results that would say 3.2 or 3.5, depending upon the functional. It would be basically all over the place. But with the correct geometry and with an optimized method that was informed by DMC, we would actually get moments that were much higher, telling us exactly about what's going on with these different spin densities in these systems. And so what we could do is we can tell you exactly where the spin is, exactly where the charge is in these systems. You might say, why would you need to do that? Well, it's exactly because you can use this information to map back to different low energy models. So many times people are interested in, can we predict the magnetic ordering in these materials? Well, we can use exactly this information to tell us exactly what kinds of exchange constants one might want, or maybe what the different moments would actually be on these atoms. So suffice it to say, what we've been able to do over the past couple of years is develop a suite of methods that allow us to clarify things like magnetism and other properties in 2D materials. Things that I should be able to tell you at some point within the next few months are results for things with spin-orbit coupling and interesting topology. So we're creating some of the first many-body methods that will actually tell you if you have a correlated insulator or not. And we can tell you that with a very, very high level of accuracy. But we can also handle things with a variety of different types of strengths of spin-orbit coupling. And so what I should hopefully have conveyed to you today is that we've been developing a variety of methods that really provide a path towards incorporating realism into model physical systems. So for decades, people have been thinking about different types of physics-based models, low-energy models, and trying to understand their behavior. But what we've been able to do is create methods that allow us to take first principles, take things about atoms, take things about electrons, and put them into those models and tell you how those models should actually be behaving, tell you what those parameters are, or allow you to just look at the material plane and model that material from scratch. And so we've shown you how we can do that at finite temperature, and so we're advancing along that direction to try to tell you what finite temperature phase diagrams look like. But we've also shown you that we can create methods that tell us things as detailed as geometries and magnetism and spin-orbit coupling in a variety of different materials. So with that, I'll thank you all for your attention. I'll thank all the people in my group who have been contributing to this work over the years. Most of the funding for this has come from Department of Energy, Air Force, and NSF. And I'd also like to thank the QMC PAC team that helped out with the last bit of work. So with that, thank you for your attention, and I'm happy to take any questions.
Questions?
Yeah, go ahead.
So the hydrogen chain, could you relax the periodicity? Make it variable?
Yeah, absolutely. So in our kinds of calculations, you can get rid of the periodicity pretty trivially by putting in open boundary conditions.
What happened?
Yeah, we actually didn't do that in this situation. So I don't know the full answer to that question because we didn't do that. But in that case, we can absolutely do. And so maybe what you're trying to get at is the differences between some of the smaller chains that people have done in the past, and ours is maybe finite size effects. Maybe.
That's a really impressive body of work you've been telling us. I was wondering if you could say something about where machine learning might be able to contribute to this development.
Sure, yeah. So that's a whole nother talk. Yeah, so as many of you may know, we've spent a lot of time using machine learning to try to accelerate these different types of methods. So we talk about very high accuracy methods, and really there's a spectrum of methods that go from relatively low accuracy and fast, like I said, to high accuracy. And so what many people are interested in is basically taking lower accuracy methods, but bringing in machine learning, the higher accuracy features to make it fast enough. And so we've done a lot of work in that area where we try to either accelerate these methods using machine learning. So maybe we try to learn potentials very, very quickly. Maybe we try to learn moves, right? So we do Monte Carlo, so that means we're sampling where different things are. We're sampling spins. And so we can use machine learning to tell us which moves to make much, much faster. But we can also use machine learning. I didn't talk about it with the geometries, but in terms of accelerating things like geometry optimization, telling us what the surface, the potential energy surface looks like. So there are a lot of places where machine learning can help. Another recent place where we used it is to accelerate dynamics for different molecular systems. So there's a whole world of that. It's not going to replace these methods, but it's going to accelerate them, is my picture of it.
Do you have ambitions to tackle the inverse problem, where I give you a bunch of properties and you tell me what material I need to put together?
Yeah. So this is all pointing to the inverse problem. So we have done some work there, and that's obviously the ultimate goal. Most people are trying to use machine learning to do that. And there are some basically generative adversarial kind of networks that people have been using in our field to do those things. We haven't spent quite as much time in that direction, but that's a whole literature in and of itself, unquestionably.
Can you maybe comment just as a follow-up? So, I've seen people speculate on everything from, using machine learning to read through the literature and sort of hunt for approaches that might be there, all the way to solving the forward problem, using that to train models to then project back. What do you think are either the strengths or weaknesses, or what do you see as, promising avenues?
Yeah, it's interesting. So, for the literature search things, it's useful for at least telling you, let's say, what kinds of methods you should be looking at, right? But it still doesn't bring the intuition about how you should put things together and why for this specific problem and how would you meld those things together. So I'd say the literature search is there in the sense that it gathers the information, but it doesn't tell you what to do with it. From the opposite perspective, I think the place where the most progress has really been made is in accelerating these hierarchies of methods, and that's where most of us have spent our time. So it's not just me. I think Andy's here. Andy Peterson has also done a lot of work here, which is saying that if we have a data set of information that gives us either computational properties that are predicted with some level of method, or we just have properties that are from experiment, taking that information and incorporating it into your modeling in a fast way has been the most productive thing so far. And so a lot of people have, this is a massive literature that's burgeoned over the past literally 5 years. Many people have used that, and it's been very effective. And so I think, at some point, it's basically going to be that every code is machine learning accelerated in that regard. So you can input some information that you have from other simulations or from experiment, and then you would run your calculations based upon that. So I think in the next 5 years, you're never going to see a code that doesn't use machine learning.
So we can continue this conversation after the talk. Because of time constraint, let's thank Brenda again for this wonderful talk.